In this video, we will introduce our work, Efficient Concertormer for Image Deblurring and Beyond. We'll explain how our approach combines global context and local detail refinement efficiently and show its strong performance across various image restoration tasks. In this video, we start by highlighting one of the most significant inventions of the decade, the transformer, or self-attention mechanism. The self-attention has become the most popular architecture across many domains. However, applying canonical self-attention to high-resolution images is highly computationally expensive because of its quadratic complexity. To overcome this limitation, several efficient variants have been proposed, such as window-based self-attention, WMSA, and transposed self-attention, which reduce complexity, but at the cost of losing part of the model's expressive power and global context understanding. While these efficient variants help reduce computation, they come with trade-offs. In window-based self-attention, or WMSA, the attention is calculated only within small local blocks, which brings linear complexity. However, this also limits the receptive field. The model only sees a portion of the image at a time. The shifted window strategy alleviates this limitation to some extent, but it still cannot match the global context that canonical self-attention provides. On the other hand, transposed self-attention computes inner products along the spatial dimension. This approach tends to mix up spatial information. For instance, if we swap any two pixel positions, the attention map remains unchanged. That means the model loses awareness of where things actually are. If we visualize the attention map of canonical self-attention, the highest values are usually located along the diagonal. This means that each position mostly attends to itself or nearby pixels. Based on this observation, the attention map of window-based self-attention can be seen as a block diagonal matrix. Each block processes only a local region without direct connection to others. Our goal in designing concerto self-attention is to maintain global connections while keeping efficiency. Thus, we propose the concerto self-attention. Here we split the self-attention into two parts, ripieno and concertino. Ripieno acts as the common self-attention, where all blocks share the same attention scores, forming the global context. On the other hand, concertino computes the difference from ripieno, focusing on the self-attention within each block. Together, they perform in harmony, just like instruments in a concerto. Since the output of a self-attention block is an MLP, we use concatenation instead of addition in our prototype because the MLP naturally takes care of the combination. This design allows concertino and ripieno to operate independently, each focusing on its own role without interfering with the other. Now, this is the overall architecture. We use a U-net as the backbone of our model and integrate our concerto self-attention within each block. This allows both global awareness and local refinement to work together throughout the entire network. Our approach performs favorably against state-of-the-art methods on both synthetic and real-world deblurring benchmarks. It achieves higher PSNR and SIM scores, demonstrating its strong performance across various datasets. This is the visual comparison on the high dataset. Our method successfully restores fine details. For example, the woman's eyes are clearly recovered, showing sharper and more natural results than other methods. Beyond deblurring, our method can be easily adapted to other image restoration tasks. For example, in deraining, it achieves higher PSNR and SSIM compared to state-of-the-art methods, demonstrating strong generalization across different restoration problems. As for the visual comparisons, our method successfully restores all textures with clear and consistent details, producing sharper and more natural results than other approaches. To compare our method with other self-attention-based approaches, our model achieves the highest PSNR while remaining efficient in terms of flops and execution time. This demonstrates that our design effectively balances performance and efficiency. Thank you for watching. We hope this video has given you a clear understanding of our concerto self-attention and its effectiveness across different image restoration tasks. Thank you again for your time and attention.